if you remember, we have to divide these guys by time when we're actually computing derivatives of the expectation value here, of the dominant exponent in this for large time. What we are really interested in when we're computing averages is derivatives of this quantity. The first derivative of the derivative, the log, this expectation value, that's what we just computed. That gave me this quantity here. One over t, limit t goes to infinity, 1 over t expectation value of our accumulated observable. And that is, by definition, the average of our observable. Because, this is just a time integral. It's time integral of the observable up to time t in infinite limit. This is just computation observable on the orbit. The second derivative is, the same story. Now we have computed the second derivative of the log. So we got that this is the limit of either the accumulated observable square minus a square, or if you want to write it the other way, it's 1 over t observable minus the expectation value squared averaged. So it says that this is the natural object because this is, you're looking at the logarithm of the partition function, which is dominated by this, and that's giving us cumulants, and cumulants are the good object because they're measuring non-Gaussian statistics. The little a must not be time observed. Little a has no time dependence. If you have time dependence in the little observable, then it's hopeless. So the idea is that we have an autonomous dynamical system. It has some property every place in state space. It's being explored by ergodic motion, by chaos or turbulence. And on every periodic trajectory, we are measuring some property. So simplest example, A was the velocity, and that only depended on the state. Our equations of motion didn't have explicit time dependence. If you have time dependence, we have to teach a different course. Because, if it's being periodically forced, we can cheat easily. We can add an extra degree of freedom if it's just one period. If it's something that's more complicated, then we have to develop a different theory which accounts for variations in time of our law of motion. So we don't have Newton's equation. We have some things that change with time, and we need a new theory to explain how they change with time. So we have to expand our dynamical system.